So what we're going to do now is take a look at some further titration calculations with a couple more steps. So we're just going to remind ourselves about how we calculate moles from mass. Remember, mass must be in grams in that triangle. And how we calculate moles from volumes and concentrations, where volumes are in decimeters cubed and concentrations are in moles per decimeter cubed. So our question that we're being asked to do is to find the molar mass, so to find the MR. We've got the mass of the solid, we've got a volume in a volumetric flask. We then put 25 of that probably into our conical flask for titrating, and it required 11 centimetres cubed of 0.1 moles per decimeter cubed barium hydroxide. So there's our barium hydroxide in our equation and our HX. The first thing I would recommend you do is try to visualise this, try to draw this out so that you can see what you would have been doing in the experiment. So I've just drawn it out like this. Okay, we were told that we put 1.32 grams of HX into this flask and we made it up to 250. That's our volumetric. We then transferred 25 into a conical. Okay, this is still our HX. And we titrated it with 11 centimetres cubed of 0.100 moles per decimeter cubed barium hydroxide. So that was the information from the previous page. So we look at that and we think, where could we start this calculation? And if I look at all the information, I have got enough information here to calculate the moles of barium hydroxide. And if I know the moles of barium hydroxide there, then I can calculate the moles of HX down here because they react in the ratio in the chemical equation. And then if I know the moles of HX there, I'll be able to work out how many moles of HX were in this bigger flask. And if I know the moles and the mass, I'm going to be able to calculate the MR. So that's my thought process. So I'm going to start where I can calculate moles over here with barium hydroxide, and I'm going to work my way back to my initial amounts. Let's have a go. So we're breaking that down. That's what we've been told to do as well. Calculate the number of moles of barium hydroxide. So the moles are very clever. So remember that barium hydroxide was the one we highlighted in green. So go back and check the data that we highlighted in green. 11 but centimetres cubed need to be converted. So we would get 1.1 times 10 to the minus 3 moles of barium hydroxide. Now we're going to use our balanced equation and our ratio between HX and barium hydroxide. For every 2 HXs, there's 1 barium hydroxide. So the number of moles of HX is 2 times the number of moles of barium hydroxide. Always use the balanced equation in your second step. Now, given that we know the number of moles of HX, this is still in our titration experiment. So if we were to look at our picture again, this is the number of moles of HX down here in our titration. That's how those two have reacted in this section. The barium hydroxide and the HX have reacted in the conical flask. And that's how many moles must be in the conical flask. We now need to work out how many moles are in this bigger flask. What section, what portion of it did we take from one flask to the other? And if we have a look, we're going to scale up. This is called scaling up to the bigger flask. So we're going to scale up. We use 25, but we want to go all the way to 250. How do you get from 25 to 250? So the number of moles of HX in 250 is 10 times. So you can type that on your calculator or work it out. Got 0.022 moles. And then it says calculate the molar mass. So going back to our triangle at the top, the molar mass will be the mass divided by the number of moles. and we had 1.32 grams and 0.022 moles. If you work that out to one decimal place, or in this case 3 significant figures, because we'll be asked for appropriate sig fig, and our numbers were given to 3, we get 60.0. So let's have a go at another one. Similar type of question. We've got 2.13 grams of a carbonate there. It was dissolved in water and made up to 100 in a volumetric flask. So let's put that on our diagram. 2.13 grams of M2CO3, and this time made up to 100. We then took 10 centimetres cubed of it, so down here there's only 10 centimetres cubed of it, and we required 18.5 centimetres cubed of 0.1 mole per decimetre cubed HCl. This is the amount of hydrochloric acid which is here in our balanced equation. So let's use that information to calculate the MR, the molar mass of our carbonate. Where can we start? Well, we can start here. We've got enough information to calculate moles of HCl. And then if we're going from there to here, we're swapping chemicals, we're going to need to use our ratio from our balanced equation. So we have a look at our ratio. We've got HCl and we want M2CO3. And in the balanced equation there's 2 HCl's for every one of these. So our number of moles of M2CO3 down here in our conical flask, so in 10 centimetres cubed, would be the number of moles of HCl. But the ratio is 2 to 1, so for every 2 we only get 1, so we're going to half it, and we're going to get 9.25 times 10 to the minus 4. What we do now, well, we're moving now from here, this conical flask, to this volumetric flask, and we have to scale up. There's more chemicals in the volumetric flask than there is in the conical. There's 100 compared to 10, so we're again timesing by 10. So the number of moles of M2CO3 in 100 centimetres cubed equals 10 times 9.25, which is 9.25 times 10 to the minus 3. And then the last little bit is, now we know the moles and the mass, we can find the MR, mass over moles, 2.13 grams divided by 9.25 times 10 to the minus 3. Put that into your calculator and you should get 230.3. Now we have to identify M. So we know that the whole of M2CO3 is 230.3. We've got 2 M's, which we don't know, plus a C, plus 3 O's, and it equals 230.3. So do a bit of rearrangement. 2 M's is going to equal 170.3. I see. So M, we're going to half that. We're going to get 85.1. And then if we go to our periodic table, we could use our periodic table to locate this, and if you do, you should find that M is rubidium, and that makes sense because it's in group 1, and something in group 1 would make a carbonate with the formula M2CO3.